My name is Tyler Prine. I'm the Phobos 2 cold gas thruster team lead. Today we'll be taking you through our system designs. So today our agenda consists of the program and project background, our program phase goals, the administrations and system engineering, the propulsion system and feed system, and then our control system and testing stand. Our program background is the compilation of several small teams that are performing research and development for our future integration into both our Aries liquid and Demos solid teams. The teams include the aforementioned cold gas thruster, the composites team, the motor clustering, and fin vectoring. The overall mission of our cold gas thruster team is to design, fabricate, test, and eventually fly a multi-purpose cold gas thruster system. This is the first iteration of our team. Instead of yearly goals, we intend to outline our goals in phases which can be completed at any time. Our current phase goals include phase 1, which we're in right now, to create a simple system to familiarize ourselves with the manufacturing and maintaining of a system. The focus will be on one-dimensional movements and using an external source for the gas. Phase 2 will consist of focusing on increasing our efficiency and adding in two-dimensional movements. Phase 3 in the future will include further experiment with three-dimensional movement and engine design.
Hello, my name is Nathan Humphrey, and we'll start looking into this phase of this project starting from an administrative perspective. First of all, here's our team that will be speaking to you today. Each of us will go into respective additions or respective components of the project as we go through today. For this project, we've broken it down into 4 subsystems: propulsion, feed system, controls, and lastly, a test stand. The propulsion subsystem, along with doing analysis from a thrust and propulsion standpoint, is also in charge of the nozzle geometry and material, as well as the thrust chamber assembly, manufacturing, and part selection. The feed system, on the other hand, is in charge of anything leading up to that thrust chamber. So that's the gas selection, pressure regulation, as well as any of the piping tubing that goes into that. The controls is where our power and electronics are, as well as our overall control system. Lastly, we also have a test system. This is just to ensure we can safely test and prove the feasibility of this cold gas thruster system. As far as for this phase, we set out a couple of requirements that we want to reach. The first is to maintain consistent hover. So we want this cold gas thruster to be able to maintain that hover, but we are, for this phase, going to restrict it to 1 degree of freedom, so just that up and down direction. We also want to make sure we're building this with upgradable components. When we say this, we're meaning that the part selection here is to prove plausibility of our design, with the idea that we can later update these components to improve efficiency or improve how well our cold gas thruster system functions. We'll also be using an external gas system. So the gas storage will not be on the actual thruster that is hovering. This is mostly to meet that hovering and reduce the weight. We'll also be having a throttleable system, once again tying into that kind of overall consistent hover goal. But we also want that throttleable system to be pre-programmed. As far as what we've completed so far, we started doing a lot of work in research, looking at possible designs, what people have done in the past, as well as what conditions we could expect our cold gas thruster to experience. Based on some of the initial conditions we found through our research, we started to do some preliminary calculations, and by analyzing these calculations, started to determine some operating parameters that our cold gas thruster system could experience. Lastly, we started to do some design work. Namely, we completed a draft of our test apparatus and also did some conceptual system work in a P&ID. Looking at overall budget of this system, right now our preliminary budget is right around $1,600. As we go into each of these subsystems, they will dive more into where these potential costs are coming from. Looking forward from an administrative perspective, we always wanted to be implementing and improving that We're refining that budget and bill of materials to accurately reflect our current design as we improve it. We'll also be developing a concept of operations diagram. And lastly, we'll want to continue to detail major technical milestones throughout this project as we reach them.
From here, I'll be taking us through the systems engineering designs. Below is our technical flowchart. We initially did some basic research on previous cold gas thrusters. From there, we did some initial systems engineering and administrative detail work. Following this, our propulsions team made MATLAB system simulations. We began basic chamber and nozzle design phases. And then currently, we're working on a component selection for our feed system and control system. The control system is working on determining a method of error calculation, and we are working on choosing a material for our chamber and nozzle, following which we will determine the final nozzle expansion angle and length. After this, in the future, we intend to do a CFD analysis on our chamber and nozzle. Using this CFD analysis, we'll take those blueprints and manufacture the chamber and nozzle. Following this, we'll integrate the control system, feed system, and nozzle system together. With this full assembly, we'll begin a low pressure leak test. Given successful completion of that, we'll do a hydrostatic pressure test. And then after that, we'll do a static thruster test. Given successful completion of the 3 of these, we'll do a thruster hover test. Given successful completion of this, we'll consider the project as being completed. This is a general system design overview. The system is going to be made of modular components, so we can substitute parts out with minimal impact to various aspects. The safety factor is going to be 3.5, as is required by the ASME standards. The working fluid source is going to be at 2.5 megapascals or greater, as is necessitated by the thruster system. We're going to regulate it down from there if necessary. The working fluid is going to be air, as it's cheaper, more sustainable, and less environmentally harmful than other options. The working fluid temperature is going to be at room temperature because the compressor will be stored at room temperature. This is our system feed P&ID. The air begins in our high pressure storage tank. The compressor flows out through various gauges, the thermocoupler and the pressure gauges, to allow us to take data compared to our predictions. We have a pressure regulator down that may be included in our compressor. We aren't entirely certain on the one we're using at the moment. From there, it flows around into our control valve, which will regulate the flow of gas into the cold gas thruster and allow us to achieve variable thrust. This is one of our initial thruster design concepts. It includes a bolted flange attachment method. There's an entry port on the top half for air to enter. From there, the system is going to be manufactured in 2 halves and attached with bolted flanges on the outside. An O-ring will be placed in between these 2 halves to minimize any potential leakage, and the nozzle will be held on by a flanged edge and pressure sealed with an O-ring. The main challenges of this design consist of the fact that the bolts will be handling a very concentrated stress and ensuring that that seal is airtight. This is our second potential design that we've considered so far. It is very similar to the first, except that the attachment method consists of a threaded connection in the center. The nozzle is similarly flanged and pressure sealed with an O-ring, and the challenges of this also consist of making it airtight and able to handle the potential pressure requirements. This is our working fluid trade study. We compared standard cold gas thruster working fluids, namely hydrogen, helium, hydrogen, and air. We rated them based on various criteria to see which would be the best option. We did safety based on the fact that air and helium are inert and non-toxic to humans. We did affordability and found that air and nitrogen systems, they're both easier to acquire and the systems are generally cheaper. The accessibility of air is far easier than any other options, as you can use a compressor, and then the system itself only has to be airtight, whereas helium and hydrogen would require being much more over-engineered as they're much smaller particles. The performance of hydrogen was found to be the highest, as it has the lowest density and as such the highest specific impulse. The fluid operation range criteria found that helium would be almost impossible to condense at the pressures we're working with, whereas air will be just below its critical pressure. Nitrogen and hydrogen were found to be very likely to condense at the pressures we need. Taking all these criteria, we found that air would be the best of the working fluids available. For our overall onboard mass estimates, we don't have a final material selected for propulsions, so we can't give a final estimate yet. Propulsions can go into this more in their slides.
Hey everyone, my name is Garrett, and I'm on the Phobos cold gas thruster propulsion system. So taking a look at our nozzle design program and assumptions, we decided to go with MATLAB as our software of choice when making some of the initial calculations that we made. Our team is much more comfortable with MATLAB than any of the alternative software, so that's what we chose. The initial calculations we made to find some of these parameters were made using some compressible flow equations to show some of the important relationships that we need to be looking at when we're designing our system. The assumptions that we made for these program calculations include adiabatic, isentropic, quasi-one-dimensional flow, a calorically perfect gas is our working fluid, which, as previously mentioned, was air, and the negligible loss through the piping and valves. So these assumptions were made for the simplicity of these calculations. Below are some of the operating conditions we used for our MATLAB simulation. As you can see, we chose 100 newtons for our thrust. We chose this because we believe that the maximum weight of our system is going to be roughly 100 newtons. So we wanted a thrust that would be able to match that and keep our system hovering. We chose an initial tank total temperature of around 300 Kelvin. The reason we chose a thrust efficiency of 90% was to keep our calculations liberal and keep the parameters liberal. The chamber pressure we chose was around 2.5 megapascals. And the last three operating conditions are based on the working fluid that we chose, which was air.
All right, so my name is Tanner Tripoli, and I'll be taking you through the propulsion system analysis of our cold gas thruster. So here we have mass flow rate plotted versus chamber pressure. And as you can see, we're currently looking at anywhere between 2 megapascals and 3.5 megapascals, which is the bounds of the larger graph here. The smaller one is the full curve from 0 to 10 megapascals, and you'll see that on the rest of the graphs after this slide. The lower pressure of 2 megapascals was selected because the mass flow rate begins to level off after this point, which means at this point the system is much less sensitive to fluctuations in chamber pressure, which will occur due to the inconsistencies with our air compressor. We chose an upper pressure of 3.5 megapascals to avoid our air becoming supercritical, and air becomes supercritical at about 3.7 megapascals, and hanging around that range is the worst place to be. We decided to select a chamber pressure first so we could begin design and structural analysis of the thrust chamber assembly. All right, here we have optimal throat area and area ratios for choke flow, both plotted against chamber pressure again. And what we can gather from this is continuing to increase the chamber pressure would mean designing a larger nozzle and a heavier thrust chamber, increasing weight. And once the throat and area ratios are decided upon, they will remain constant, unlike the other variables in these graphs. Right, here's exit velocity and exit Mach. There's not much to be said about these, but they do show that chamber pressure is directly linked to specific impulse, as exit velocity is directly proportional to ISP, and as chamber pressure increases, so does exit velocity. All right, so here we have a simulation for a single point in our MATLAB code. So for this, we chose a thrust of 100 newtons and a chamber pressure of 2.5 megapascals or 360 psi. We chose this chamber pressure just because it's well below the critical point of air. And so plugging those into our MATLAB simulation, we'll get an area ratio of 3.3, a throat area of 2.6 times 10 to the negative fifth meters squared, and exit area of 8.5 times 10 to the fifth meters squared, an exit Mach number of 2.74, a mass flow rate of 0.15 kilograms per second, and an exit velocity of about 600 meters per second.
Sorry, I was muted. So looking at the potential for the nozzle integration technique, we have decided that we're going to go with a conical design for the nozzle. However, we have not decided officially how we will integrate this nozzle with the chamber. Currently, we're looking at using either a flange attachment, as Tyler mentioned previously, and we're also looking at a threaded attachment. We have not completely decided on which one we will go with yet, but we will be looking at this in the future. So taking a look at the propulsion budget estimate, you can see that the weight obviously is to be determined. This is because we have not selected a material yet for the nozzle or the pressure chamber, and we also do not have many of the specifications like the size of the nozzle and the pressure chamber. Our propulsion system is still very much in the conceptual phase of the design. So aside from our initial calculations and some of our parameters, we're still very much looking at finalizing what the nozzle and pressure chamber will look like. These price points that you see here are based on what we think would be sort of an upper limit to the threshold of what we'd be paying for the materials for the nozzle and the pressure chamber. These are based on some of the sources we found looking at manufacturing these out of an aluminum alloy. We have, like I said, we have not fully decided on that, but this is what we're looking at, what we think will be an upper limit to that threshold. So moving forward with the nozzle design, the first thing we'll be looking at is obviously the material selection for the nozzle and the chamber. Once we finish that, we'll be looking at making a MATLAB code to find the expansion angle of that nozzle and looking at the length of the nozzle as well so that we can begin looking at manufacturing the nozzle and the chamber. We will also be considering the thermal analysis as well as the structural analysis of the thrust chamber assembly before manufacturing using some CFD analysis. Once we manufacture, we'll be looking at the pressure vessel testing for leaks, and testing to ensure that the pressure vessel can handle the high pressures that we're going to be putting it through. And then we'll follow that with a static flow test before we get to the actual hover test.
From here, I'll be taking you through our feed system. A large portion of this was already detailed in our systems engineering. So for our feed budget, we've put down an air compressor at 0 because we intend to borrow one from a professor on campus. We have a pressure regulator at $400. We hope to have one integrated with the compressor. However, if that's not possible, that's the estimate we've gotten. We have the actuating valve that controls will require to maintain the variable flow later. We have our various hosing and fittings that we've approximated to cap out around $200, and the onboard weight from this will be 500 grams. The various instrumentation, being the pressure gauges and the thermocouples, we've put down as about $250, and the onboard weight estimate will be 100 grams. This brings the overall feed price to about $1,250 and the overall onboard weight to about 600 grams. For our feed system future considerations, we need to go through valve selection and the analysis to ensure that there's no failures throughout in the piping. We need to weigh various piping material and geometries to determine a material that's non-restrictive, yet also strong and cheap enough for our goals. We need to analyze the pressure and attachments at our key joints to make sure that there's no possible weak points where it could fail. And finally, for our integration, we need to ensure that the piping can smoothly integrate with the testing apparatus.
I'm Rector Von Clark. I'll be taking you through the control system. The main objective of the control system is to actuate the opening between the nozzle and the pressure vessel, allowing us to precisely control thrust during flight in order to increase or decrease the altitude of the assembly. The acceleration will be measured using an inertial measurement unit, which gives greater precision in controlling altitude than measuring chamber pressure data. We'll be coding the software for the control system in C++, as compilers for C++ run faster than other languages, which is suitable in a time-sensitive application. Here's the hardware block diagram. The main controller receives data from the IMU. From here, the necessary adjustment to the valve is calculated and passed through a motor controller or H-bridge in order to use the valve actuator. Here is the code flow diagram. When initially started, a timeline with the expected positions and accelerations is loaded. This timeline is used by the PID controller, roughly represented in the diagram, in order to compare the assembly's current position and acceleration. Once the timeline has finished, the code slowly shuts the valve in order to safely stop gas flow. The main source of mass is the breadboard for controls with a price of $5. The main controller, 15 and 0.32 grams. The IMU is also $15 and the mass is 0.28 grams. And the motor controller or H-bridge is expected to be $5 and 0.5 grams, giving a total of $40 toward our budget, and slightly under 80 grams. For the control system's future considerations, the best method of calculating positional and acceleration error from IMU data needs to be determined. Additionally, once a valve is selected, the necessary voltage and control signal to actuate the valve will need to be adjusted. The code diagram needs to be refined, breaking general steps into their more precise component functions. The diagram also needs to show which processes are sequential and which ones can be run in parallel. Finally, an important consideration is determining safety conditions in the code to trigger shutdown in the event of failure.
Hello, my name is Ian Seals, and today I'll be taking you through our testing apparatus. Okay, so we decided to build a test cage to house our cold gas thruster. The cage is designed to safely test the hovering capabilities of the cold gas thruster. For our first design iteration, the test cage will feature a center rail system. The system will restrict motion to 1 degree of freedom. It also allows for isolated testing of the engine's ability to control thrust level with simplified closed loop feedback, and parts can be removed to test for stable hover with additional degrees of freedom in the following design iterations as previously mentioned. So here you can get a nice 3D view of what we are picturing our test cage to look like. It is designed out of wooden frame, chicken wire, and a metal retention system. The thruster will run along wooden rails in 1 dimension, like you see there in the center of the diagram. The wooden and chicken wire cage will hold the engine rail system in place, and the cage can be latched closed for safety. The outer cage itself is 6 by 6 by 6 feet and can be used for future tests both in and out of the cold gas thruster program. So here we have a short video that shows you how the wooden rail system and metal retention system will work with the engine. And you can see a closer diagram there on the right is still. Our overall budget estimate, the chicken wire and boards, we both estimated to be around $50. And miscellaneous, that's just if we run into anything else while building this that we think we might need, such as bearings or anything else. And we give that around $50 in case there's extra money. And that brings our total for testing to $150.
Thank you for listening to our presentation. If you have any questions, we'll gladly accept them.